welcome. It's always pleasure to come here and discuss a lot of things with you. And what I'm just trying to do, let me explain it why I am interested in projective. What was the problem? See, like other symmetries, the symmetry is something. If you just have a sum map on something, it's going to be invariant. Sometimes people say it's identity map, but it's not identity map. It's something else. It's a transformation. So see, why I was interested? The first symmetry paper comes in 1969 with Carson and other people. And the people start looking at that and they produce number of papers in terms of isometries, in terms of conformals, in terms of the homothetic vector field, affine vector field, and filling and unit. But the projective stuff seems to be ignored. Why is the problem? I will show it to you where the problem. The problem was, if I just show it to you, this equation, that's the equation. That was the equation of the problem. See, the question was how to find, how to find HAB.
So the first line there is not it's not isometry.
Well, no.
The first where you're going to read the derivative.
Yeah. This is, I will explain it later. Okay. Let me say this is where we need to find some HAB and then one form. That was the question. And can you imagine? People took more than 30 years and they could not solve it. One day I was with my professor and then I asked him what he was trying to do. He said he is working on projective. That was in 2001. I said, what do you mean by projective? I learned it before he finished, I finished it.
Oh, okay.
So let's see what type of techniques, what I did basically, I did, if the rank of the space-time, you have a space-time, you can calculate the curvature. You just calculate the curvature, you just write it in 6 by 6 form. If the rank of the curvature is 1, 2, 3 or 4, no proper projective exists. That I proved myself. So what's happened with the rank 5? It took me around 4 years, I could not solve it. I don't know when I'm just going to solve it, but for the rank 6, I did it.
So those that are rank 1 to 5, there's no...
Rank 4, 1 to 4.
1 to 4, there's
no proper projective exists.
So give me an example of...
I will give you. I will give everything.
On a well-known space-time that has...
Everything is a general. Any space-time. You just to take any space-time.
Just with the rank?
Yeah. I proved it generally. It's not only special. I proved it generally. It's hold for every space-time. Let's see. So that was a little bit introduction. So I'll just start from here. See, throughout in this talk, I'm just assuming the space-time, which is our manifold, is connected, Hausdorff, Lorentzian signature with Lorentzian matrix is usual, because there are a lot of physical meaning of Hausdorff, a lot of physical meaning of connected. If you do not have connected, you cannot send a signal. Hausdorff means you have only unique point. If there is, you cannot have 2 points because of different point of view and different reasons. Then you can talk about paracompact, the other different things. I'm not going to discuss. So the metric basically comes from here. There are a number of people. So see, this one is metric. Lorentzian metric is there. A lot of people are asked where this metric comes. Basically, it's a solution of Einstein field equation. How you find the Einstein solution is a long story. So I'm just going to assume the metric is here. One can find the metric with different reasons as well. See, the curvature tensor, this one, is come from the Lewis-Waiter corrections, basically which people call Christoffel symbols, and the Riemann tensor, one of this. Now the people ask, is it any possibility your covariant derivative, the Christoffel symbol comes from somewhere else? Yes, it can be. It can come from the covariant derivative, but we are not interested in covariant derivative. We are interested in the Lewis-Waiter corrections from the G-metric tensor. That's the usual notation. your Ricci tensor, usual covariant partial derivative and Lie derivative denoted by comma, semicolon, and then out. So what I'm assuming here, my space-time is not flat. If the space-time is flat, so we already knew it, it exists 24 proper projective vector fields, so it's not flat.
Minkowski, for example.
Yeah, it's 24. How 24? You can easily see it. There is a factor involved HAB 10, FAB 6, 5, and then X altogether 24. And then
The 10 are the isometries.
10 are isometric
vectors.
Yeah. And then you have a 1 homotopy vector field, 9 proper conformal, and 4 proper projective. So altogether 24. You can count it like HAB, FAB, 5, and X. They are altogether 24.
For the Minkowski.
For the Minkowski. So now just going to start is what I did is all general. Pick up any space-time, all general, and then as you ask particular example, I give a particular example as well. How one can find it. That's the usual. If you have any vector field on M, one can easily decompose it. And this bit is a second order symmetric tensor, and this is second order skew symmetric. And most of the work basically done from this people called it bilateral. See, that's what I wrote it. Symmetric tensor and this one is skew symmetric. So the vector field, here is a lot of geometry and other things will come. If you want to say, I can explain it in a minute. The vector field X is said to be a projective if the local diffeomorphism is a psi-T map, which map geodesic. Basically, it's going to preserve the geodesic structure. It's going to preserve the, but not the affine parameter, which is T. So that's the physical meaning, because a lot of the pure mathematics are differential geometry people, what they will say, there is a manifold, there is open set U, by T of U, you need to find the matrix which is going to preserve according to that vector field X, which is phi T. People call it pull back map or push forward map, whatever the people say. You're surprised to know that this thing is derived by Eisenhardt in 1927 by using that definition, 1927. And that was a problem in the first instance, how to solve it, because we do not know how to calculate it. And this is HAB semicolon C, and then how to form one form. Now see from here, if I just say this is a local gradient of this eta, see if we are able to find some x which is going to satisfy this equation, then what we call the problem. Now see,
So that then is the actual definition of a projective.
that's right.
It's a map that maps geodesics
To geodesics and do not preserve the affine parameter. Which is affine parameter you say sometime S, sometime T. No, that's the affine parameter.
the arc length parameter.
That's not.
It does not preserve.
Does not. It must not be the same. If it's going to be the same, that's going to be affine. In that case, I'll show it to you. You look at that. If this is going to be whole, this is going to be whole, then people called it special project. And look at that. You will get the definition. What's happened? If it's going to be this bit, eta C is equal to 0, then HAB semicolon C is equal to 0 is called people affine parameter, affine vector field. And then I made a lot of progress on the affine one. That's because of me, I did number of papers produced on the affine as well. So see, that's what the definition of proper is. That's what it said. Then if you have C, HAB, that one is this equal to 0, then you can call it affine vector field. If further, if it's going to be whole, you know it, then this is called homogeneous. Then if C is equal to 0, then you can call it.
The homosexuality, that is a constant, right?
That's right.
The vector.
That's right. That's the constant. That's why I just label it C is equal to R.
Ah, okay.
So see, so for proper projective mean, you don't have a eta C is equal to 0. So that's important. That thing is very important. That's question 3. Because it tells you the rank. How it tells you the rank? If it has only one solution, this bit, only one solution, then the rank is 3 or 2. If you have a 2 solution, then the guaranteed rank 1. If you have a no solution, then you have a rank 4, 5 or 6. If you have 3 solutions, then rank 0. If space time is blank. That basically comes all the bit from algebra. That comes from all the bit from algebra. One can easily prove it. And I did something by using that equation. So now the skew symmetric tensor, SAB, people call it bivector. And you know the well-known theorem, if you have a 4 by 4 skew symmetric matrix, it always have a rank even. It can be 0, 2 or 4. It cannot be 3, it cannot be 1. So if this is going to be 0, FAB straight away 0, no use. And if it's rank 2, then people call it it's a simple. If it's rank 4, then people call it it's a non-simple. What do you mean by simple? Simple means, you can easily say, simple means, what is FAB? FAB. It's a two-dimensional subspace of tangent space. If it's two-dimensional, so it has a plane. Blades mean it's spanned by 2 vectors. If both are space-like, then the bivector is space. If one is null, the bivector is null. If the both are null, then the bivector is timeline. That's the way it's defined. So now think about that's what it is. I just skip all these details because I cannot cover all these details here. Then now pick up a tetrad, also normal tetrad, with that TA is equal to -1, then the rest x, y, z, their inner product is 1. One can define 6-dimensional vector space of the bivector by using this. And if it's going to be simple, it's going to be like that. If it's going to be non-simple, think about it. It has a space-like blade, it's a time-like, and it's a null blade. So, as I told you, it was really difficult. It was really difficult to handle this equation. So, alternate techniques need to be. So, first alternate techniques came basically in 1983 by Alan Barnes, Southampton guy, and there he found by using not algebraically but computer stuff, he produced there are dimension is 24, and then he did it. That was for Alan Barnes, and then the Professor Hall and McIntosh, they took that thing from there and used this stuff and then proved this. And then there is well-known theorem of McIntosh and Hall. Then from there it's going to be easy. It was never ever easy for me. And another thing is, whenever I was doing PhD, my supervisor, it's not your job. Go to the library, you find it for me. But we are, I say, so see, start from here. It's identity. Just take the d derivative and use this information, you will get that. And what is this? I will kindly see it. This is very important for calculating. This is eigenvector of this Riemann tensor with eigenvalues lambda. This is eigenvector stuff. And a lot of people thought the eigenvalues are always constant. It's not constant. It's a very difficult function. Now, look here. This expression, you can simplify it. It's very easy. Just give you some close relationship between PAB, it's a symmetric tensor, and this FAB is a skew symmetric. What type of relation you will get from here? Now, see the result. What I do use the result, this is a beautiful result. If you have a symmetric tensor and the skew symmetric tensor, the eigenvector of this have the same eigenvalues. That is the result they proved it. And it looks very simple. It's published by 1980 by Ghulam. So what we are saying, we have a symmetric tensor and this is skew symmetric. If you have a, this is bivector, it has two. It's a simple bivector spanned by two vectors. If it's space-like, then their eigenvector of this have the same eigenvalues. That's the result. So that things of knowledge I needed to produce something. Now think about. Now I'm just going to say what's my main result. See, just take any space-time of rank 1. Look at that. If a space-time is rank 1, then there are total 6 bivectors. 5 bivectors which contract this Riemann tensor and give it to UC. And then you can write Riemann tensor in terms of bivectors, you will find that relation. And then from here, you just take this equation 8 and make the use of equation previous one. I can easily find it. Eta A semicolon B is equal to G. Now just take the rederivative and then contract them. You will get the expression for HAB is that expression. Now this expression, take its semicolon and then put it back in equation 2, and after connection you will get that. This is going to be, and this implies eta is constant, eta A comma A is equal to 0. It's no proper project.
So this procedure they must go rank 1, rank 2, rank 3.
But rank 1 is easier because you have more freedom. Because you have a 5 bivector which contracts the Riemann tensor equal to 0. But for the rank 3, you have only 3.
What about rank 2?
Rank 2 will come later. It's a little bit dodgy. That's why I just put first the rank 3 and then rank 2. Now see it. Here again, following the same procedure. And then you can write it like that, and then again you will get HAB semicolon C is equal. It took me for each case around 5 months to do all this algebraic manipulation, all these things. But thanks. So see, on the same using the same procedure, I will find it, and then again take this covariant derivative and plug back in equation 2. You will find it again the same stuff. So it means whenever you give me a space time, because I personally believe mathematicians are lazy in my case. So they want to know which thing is this where. So I knew it in this special case, if I have a rank 5 or 6, project exists, otherwise no. That's what we are planning to do, some work with Professor as well. Do something in FRT theory, to extend all these things, which become a little bit easier if one once understand this. And then our stuff.
So you said the Minkowski is rank 0.
Minkowski is rank 0. So it means you have
then it jumps from rank 0 to rank 5 before you get projected.
There's nothing. But in Minkowski, we don't assume it because it has 24. So it's a trivial. For the non-trivial stuff, you have to jump it to 5 or 6. The calculation I showed to you, which I made for rank, 4. So you'll see it.
So I would imagine there's no well-known space-times that have rank 1, 2, 3, or 4.
No. I will show it to you in a minute. See, it comes basically from the decomposability. You know, if your space-time is 1 plus 1 plus 2
so you look
decomposable.
at proper project.
That's, yeah.
Not just projective.
No. Projective means it can be killing.
Yes,
It can be overtaking. I'm just talking about proper projective.
Yeah, otherwise it's okay.
And one can easily see if you just have a decomposability or holonomy or other things as well. You know, people discuss all these type of things by using. See, I was the only one who just talked about the rank. Previously, a lot of people talked about holonomy, decomposability, and then once you talk about holonomy and decomposability, there are a lot of problems. I will show to you. Sometimes space-time is 1 plus 3 decomposable, and they said the rank is 3. But I can show the space-time where the rank is 1 after. That's a famous one. So that's the problem. So instead of getting rid of all these problems, I just start talking about from the last 10 years. See, rank. This is much more convenient for me because otherwise this is makes something like difficult. So see, that's what this is talking about. Yeah, that's ranks 2. If you have rank 2, this means you have a 4 bivectors. Knock it out to be 0. And again, by following the same procedure, I'm not going to discuss, it's a following same procedure, you can again find the no proper projective. Then I thought, it's enough. Now I just give some example. Now this is the example which we were talking about, the rank 4 one. Yeah, I just took the example and then how I made it rank 4, I'll show you. So this is working on some example. It's rank 4. Now see, this is a famous plane symmetric space. Is a line element like that, it exists, 4 Killing vector fields, and Sigri type is like that. So the Riemann tensor component 2 up, 2 down is like that. So now the possibility of this one is rank 6, 5, 4, 3, 1. There is no possibility when the rank of this space-time is 2. So I needed 4. So what I did actually, I just made this is equal to 0. What I did basically, this is going to be equal to 0. And then I will get the possibility of this. I just make it eigenvalues, eigenvector problem with lambda 1, lambda 2, lambda 3 z, and the rank of this space. Have a good look. The rank of this space-time is, as you said, 4. Yeah. So you can make any space-time rank 4, and it's 4.
So, for example, this could be short shell.
Yeah. You can use it. Short shell is rank 4. So it's no problem projecting. Me and Anand Koshi paper 2004 International Journal of Mathematics short shell and PLA. That's what we proved. We did it in 2004. Then
I suppose the curve matrix will be the same.
Yeah. Curl matrix is a rank 6 matrix.
6?
Yeah. Curl matrix is a rank 6.
So it does get proposed to that.
No. For rank 6, you don't know. You need to calculate. It can be.
So you don't know whether it
exists or not. Yeah. But it's guaranteed. You can never knock it out. You don't have. Because but you knew it. Rank 1, 2, 3, 4. No problem. It's rank 6, there might be. But you need to have.
So for the curl matrix, it's still not known.
People did it generally. They said there is no proper projective. That was.
It has to be 2, I think, killing vectors, right?
Yeah. That's Hall in 2001. Alan Keen, who proved it in journalism. They wrote it a couple of pages paper. And then, look at that. It was how difficult it was. Look at that. See, the eigenvector of curvature tensor with the blades this, and with the eigenvalue 0 with the blade that. You can easily. I just going to keep this thing and give it to you, show it to you. The result is going to be like that. Now you just subtract it, and do some manipulation and contract with the bivector you will get, I'm just keeping these things, and then you can find that. Sorry, because we had a long debate about this, I'm just going to skip this thing. I don't want people feel much bored. Well, I did it maybe how many years, I don't know, but look, so this is HEB. Then what I did, it's the rank 4. I just take its covariant derivative and plugging back and using this information. I will get the information on C, B, and E. This is going to tell me C is function of Tx, eta is function of Tx, and then say E is function of P only. Therefore, then we are, after using all these algebraic manipulations, I will reach there. So what I did, I just write TAB in terms of orthonormal basis, and then use this concept. TATB is equal to 0, and then plug that. So I reach there with this expression. And after this expression, see, from here, I was really stuck. What to do with this? Now, what I did, I just contract this equation with this thing and this thing. Now you can see it. I just took this linear combination. I just write it like in terms of HEB. Now see, HEB was my simple bilateral. So it must be, if the left hand side is simple, the right hand side must be simple. Then I just choose one of them is equal to 0, this and equal to 0. This HEB is bivector and H star is a dual bivector. It's going to be contract is equal to 0. Then what you will find at the end, the eta is going to be a TAB is equal to, then I just plug that, is going to be eta is equal to 0. Again, I just proved it. For example, for the rank case, the only thing you have, you don't have a homothetic, don't have a fine, but you have a only killing vector figure the rank. Basically, that was the giving the example. If your rank is 4, no proper project. And then this paper,
Where's the 5?
that's what we said. It took me around 5 years. I cannot prove for the rank 5. Still open question if somebody helps me. And this one, you remember, in the rank 6 case, we did it.
Yeah, the blanket
type one, we did it. And then by using the rank stuff. But the rank 5, I could not solve it. But the rank 6, look at that. That's a particular example I chose.
So that would include FRW as well.
Yeah, that's right. It's everything. Yeah.
The time.
Yeah, you will see it comes. Now it's a rank 6 case. Let me, for your, see, I am going to consider some particular symmetry. Symmetry means I'm just going to consider some vector field which preserves something. That symmetry is going to be just, which I was going to talk about, the symmetry which preserves the geodesic structure, but not the fine. That people call it projective symmetry. So what I achieved or proved differently from the word. See, I just proved if the rank of the spacetime, that spacetime which comes the curvature, if the rank of this one is 1, 2, 3, 4, no problem. That particular symmetry. If the rank 5, I could not prove it, and nobody else at the moment. And if it's rank 6, then it has. The most important thing you see, if you have a degeneracy in the Riemann tensor, that's become easier. If you do not have a degeneracy, then there is a problem. Because degeneracy means you can have enough information. Degeneracy means you have the same eigenvalues. If you have same eigenvalues. Now, think about in the case when the rank of the space-time is 6, then the blanket type 1 space. It's admit 3 linearly independent killing vector field, people call conservation laws. Now, see, look, it's how difficult is this for me. That's why I choose it. All have 6 different eigenvalues. Totally different eigenvalues. All of 6 different eigenvalues. If you have 6 different eigenvalues, it's very tough. That's why I choose this. If you have a degeneracy, then it's become easier. And then what we do, see, look at that. I just label them, these bivectors. P stands for 0, 1 stands for X, 2 stands for Y, and 3 stands for Z. 0 means XT, and then similarly there. And then I just label them. And then we choose the category like that. Now see how I choose it that. I just choose this one and alpha 5 and then alpha 6. These are the bivectors with that eigenvalues, and this one is the bivector with this. Then I can write it like that. After contracting all this work using the completeness relation, I just write it like that. Now I assume that both eigenvalues are not same. If the both eigenvalues are not same, I just subtract them, I will get that expression. In 2002, people are able to write like that. Now still the question was how to find the vector frequency. Now you can see it. HAB, as I said, this is so the component of HAB is like that. Now use the definition of this. If I use the definition of this one, then I can write 10 non-linear, highly coupled partial differential equations. And that was really terrible for me to solve this. It's all, unfortunately, still we don't have a computer stuff which you can do it, unfortunately. But I solved it. Do you know how many pages I spent on the calculation?
Yeah.
Roughly 300-400 pages. Shit! See, that's what it took me ages. And then there is only useful way to find the projective stuff at the moment is that. Still, yeah.
But it's not anything to make those.
It's highly non-linear. I tried it. It saves my lot of time. Then one can do it, maybe after a month instead of 1 year. In a month, one can have a good paper. But it's not. If you can, we'll try. Yeah, we'll try.
And of course, you're looking at general functions.
That's right. These are the general.
Yeah, and you maybe classify them according to the function.
That's what I'm saying. That's basically the classification. It comes down. So you got the
F, G, and H. The functions are equal.
They are only the function of t.
Yeah, but is the three functions are equal?
No,
here we are. If F, K, and H, then you got the FRW.
Yeah, if they are equal, fair enough. But in general, they are not equal.
Yeah.
Then that's the classification what we need to make. So see, I skip all the calculation. You must not terrify that. Just I reached it. Just give them clue how to solve it by using the direct integration technique, and then I just wrote it. There is the only possibility when it's going to be existence.
Which is exactly the FRW.
G is exactly the FRW. K is equal to 0. Flat. And then you can see here the form of the metric coefficient is like that, and then you have a 6 killing vector fields, and then
so
your vectors, this is the extrapolation, and then eta is like that, and your H is going to be take that form.
So then 45 is the additional, the proper projector.
Yeah, after reducing the killing vector fields. That was the proper. And then I just wrote the proper
that
form.
looks like scaling, eh?
No,
it's not scaling.
No, it's not. Look at that here. HAB, D1 is like that, D2 is like that.
Actually, if you put, you can't put C1.
No, but you can put C. Yeah, you cannot.
Because
See,
it's not changed. Okay, so I was
yeah,
thinking
it's not comes like that. You know, if you have a free space and the projective basically comes from here, and then there is something on the projection as well. But you cannot choose it. You cannot choose it. So now I just consider other cases, you know, because I just made all the classifications. Basically, we now think about when the eigenvalues are same, then I find it only projective vector fields are just scaling vector fields. Now the case when one of them zero, I just discuss each and everything here. I just set each and every case here, then you can see it here. This coefficient is 1. This space time is 1 plus 3 decomposed, and the rank is 1. So straight away, no proper projective, the only projective vector fields are affine and this proper affine vector fields. So it means proper affine means that the difference between two is proper affine preserve the geodesic structure with the affine parameter. And similarly, we have rank 1. Is that, as I told you, the rank 1 is space-time is like that. It's 1 plus 1 plus 2 decomposable. Again, we knew the theory, there is no proper projective exist. Yes, again the case is that there is no proper projective, and that's the space. And similarly, there are lot of other cases exist, which I haven't mentioned it, but I just wrote it here. You know, is this one is again 1 plus 3 decomposable, and then but you have all these calculation again 1 plus 1 plus decomposable space time. That's the whole classification. What I basically did. I just mentioned only few references. Basically, the idea behind it, maybe you people can help me to go through the rank 5 one.